Now we have defined first law, second law, and third law. So having defined all of these laws, I'll just recap the statement of third law. So what was the statement of third law? That at absolute 0 Kelvin, that is the so third law defines the absolute scale of temperature. Now at the absolute 0 temperature, all perfect crystalline substances have the same entropy, and the value of the entropy is 0, right? So all perfectly crystalline substances will have 0 entropy at absolute 0 temperature, right? As at 0 K is equal to 0 for all substances in perfectly crystalline form. So this is what we know. Now as as you can see here, now you have first law, which is the conservation law, and then you have second law, which defines entropy, directionality, or irreversibility of a process. Now you have third law, which tells about the absolute 0 temperature and also gives you a way to define absolute entropy. See, in general, what we basically measure is the change in entropy, change in energy. So we are basically interested in the change, not the absolute value. However, like delta S. So if I want to know delta S or delta U for a process, right? Now, when I'm talking about delta S from 0 to T, if you remember the integration, because again del Q equal to, again it's a reversible, equal to TdS, and if you do it at constant pressure, this is equals to dH, which is Cp dt, and Cp itself can be a function of temperature. So ds equals to Cp dt by T, and Cp itself can be a function of temperature. But when I integrate from initial state to final state, or Ti to Tf, I require to know what's the value at Tf, right? So I require to find out the value of Tf, but I require to know also the value at Ti, right? So the point is, when I have this ds, so it is basically S. So if you look at the left hand side, it is S of final state minus S of initial state. Now at that, so the value at Si, so for example the previous problems you have seen, you have some quantity like S0, right? So that is the or SM0, right? So molar entropy at 0 Kelvin. So here, once you have third law, so you can basically calculate the or estimate the absolute entropies. How? Because you will do the same integral delta S from 0 to T, but now it is at 0 and it is at T, and as you know, S0 equal to 0. Now S0 equal to 0 basically gives you a way to define standard entropy at some temperature, which is defined as S phi T or S0 T, right? You often define it as S phi T or S0 T, which is a standard entropy at temperature T, and this is basically called third law entropy. And this S0 T, we generally, for example, it is often reported for different substances. We report S0 298. 298 is your room temperature, right? 25 degrees Celsius. So so for example, this is the standard entropy at room temperature for different substances that are listed here. So if you see, these are the different substances listed here, and for these different substances, when I want to define the standard entropy at 298 Kelvin, I am basically using the fact of S0 equal to 0, right? And then for graphite, say for example, I will graphite solid, which is a solid form of carbon, one of the allotropes of carbon, which is which you will later see is the most stable allotrope of carbon, is having entropy, standard entropy of 5.7 joules per mole Kelvin, defined at 298 Kelvin, and then diamond has 2.4, water in the liquid state has 69.9, and hydrogen has 130.7. Right, this is and as you can see here that the trains look fine, because in solids the entropy, the standard entropy is also will be less, in liquid is higher, and in and in gas it is much larger. So now if you have that, now think of a process. And one of the very well known processes that is often cited in the literature or in the textbooks is the formation of silicon carbide. And what is there? We have pure silicon and you have pure carbon, and you form silicon carbide at a given temperature. However, you are thinking of a process like this. You have, if you think of the process, now from 0 Kelvin, I am at 0 Kelvin, I have silicon and carbon, is a pure form. Now I take it to a temperature of 1500 Kelvin from 0 Kelvin, and that is my my stage 1 of the process. And at 1500 Kelvin, silicon and carbon combine to form silicon carbide. That is the stage 2 of the process. So at 1500 Kelvin, this is the stage 2 of the process where silicon and carbon combine to form silicon carbide. Now I take this silicon carbide at T1 equal to 1500 Kelvin. So this is a hypothetical experiment because I cannot really go to 0 Kelvin. So, but you go to, so now you take this silicon carbide and take it to 0 Kelvin, say from 1500 to 0. Now at 0 Kelvin, silicon carbide can say decompose into silicon and carbon, because silicon carbide, silicon, carbon all have, remember here in the perfectly crystalline form, silicon carbide, silicon, carbon all will have the same entropy, and the value of entropy at 0 Kelvin is 0, right? So this is the fact that we will want to use. Okay, now if you look at this entire cycle, which contains 1, 2, and this is process number, stage 3 of the process, and this is the final stage 4. So you have 1, 2, 3 and 4. So basically the total change in entropy, delta ST, is the total change in entropy during this entire process, right? What is the process? Silicon and carbon you take from 0 Kelvin to 1500 Kelvin. At 1500 Kelvin, silicon and carbon combine to form silicon carbide. Now stage 3, silicon carbide is taken from 1500 Kelvin to 0 Kelvin, where silicon carbide can turn back to silicon and carbon, right? Can compose into silicon and carbon. And we start with 1 mole of pure silicon and 1 mole of pure carbon. That's your system. And the total change in entropy is equal to change in entropy in stage 1 of the process, stage 2 of the process, stage 3 of the process, and stage 4 of the process, right? There are 4 stages of the process. Now, remember, heat capacity of silicon carbide is different from that of silicon or carbon. Silicon has a different heat capacity, silicon carbide has a different heat capacity, carbon has a different heat capacity. Again, carbon in different form. So what is the form? Let us assume that we have taken carbon in the form of graphite, right? So silicon and carbon in 1 mole you have taken, and carbon is in the form of graphite. But all of these, silicon carbide, silicon and carbon, this is the most important point, will have different heat capacities, right? They will have different heat capacities. Now see, at delta S4, right? That is the thing. Delta S4, the stage 4 of this entire cyclic process is taking place at T equal to 0 Kelvin. At T equal to 0 Kelvin, silicon carbide individually has an entropy of 0, right? And silicon also has an entropy of 0, and carbon has an entropy of 0, right? So the change in entropy in the stage 4 of the process is basically going to be 0, right? So that's what I have written here, delta S4 equal to 0, because the entropy of pure silicon carbide is the same as the entropy of silicon and carbon at T equal to 0 Kelvin. SSIC is the entropy of silicon carbide at 0 Kelvin. So in brackets I put 0 equal to SSI at 0 Kelvin at SC at 0 Kelvin. This is the entropy of carbon, and these are all equal to 0. Therefore, delta S4 is 0. So now you have delta ST, which is delta is a cyclic process, right? It is a cyclic process. So now it's initial state and final state, right? So ultimately delta ST should be equal to 0. Now delta ST for a cyclic process that is the delta S total, is also 0, right? It's a cyclic process. My initial state and the final state are the same, and entropy is a state function, right? So now delta St is 0, delta S4 is also 0, so delta S1 plus delta S2 plus delta S3 is equal to 0. Now think of delta S1, right? Think of delta S1. What you have is silicon, delta S1 is silicon and what is the process? You are going from 0 to T1, right? So the change in entropy is S of silicon, pure silicon at T1 plus S of pure carbon at T1, right? S of pure silicon at T1, S of pure carbon at T1 minus S of silicon at 0 Kelvin and S of carbon at 0 Kelvin. Now these are 0, right? This is equal to 0, this is equal to 0. So basically delta S1 is nothing but SSI plus SSC at temperature T1, right? Now delta S2, if you see this equation, you can write delta S2 equals to minus delta S1 minus delta S3. Now let us look at delta S3. Delta S3, if I look at delta S3, you have formed already silicon carbide, right, in stage 2. Now in delta S3, you have basically taken silicon carbide that is formed and taken from 1500 Kelvin. So 1500 Kelvin is your initial temperature here and 0 Kelvin is your final temperature. So SSIC at 0 minus SS, the entropy of silicon carbide at T1, right? That is your initial. So that is going to be equal to, again, SSIC at 0 is 0, so it is minus S, right? So delta S3 minus SSIC. Now if you see now, delta S2 from this equation that you have here, let's call it A, from A, what can we write? Delta S2 equals to minus delta S1 minus delta S3, and this delta S2 is the entropy of the reaction. What is the reaction? Silicon plus carbon at stage 2 at 1500 Kelvin on silicon carbide, right? That is the, so this is basically the entropy of reaction. Now the entropy of reaction is nothing but minus delta S1 minus delta S1. Delta S1 is minus SSI minus, plus SSI plus SC. So minus delta S1 will basically be minus SSI and minus SC at T equal to T1. And minus delta S, and there is minus delta S3. Delta S3 is minus SSIC. So there is a minus sign here, there is a minus sign here, it becomes plus. So it becomes SSIC T1 minus SSI T1 and SS as an S carbon T1. So as you can see here, the delta S reaction basically exactly tells you the same thing, right? It is product, entropy of the product minus entropy of the reactants at T equal to 1500 Kelvin. Entropy of product, what is the product? Silicon carbide minus the entropy of the reactants at T1 at temperature T1, right? And as you can see, we are using this process of this understanding that of third law, that at in stage 4 where you have silicon carbon and silicon carbide, all of them have 0 entropy in the perfectly crystalline form, right? And that this is the way we can basically relate delta S2 to delta S1 and delta S3. So this is the idea, and this is how third law basically gives you a way to define the absolute entropy or define the standard entropies, right? So this is something that you can understand even in this the reaction that we consider of silicon and carbon forming silicon carbide, right? How we are making use of third law, right? Now we are always considering, say, some equilibrium, right? We in thermodynamic equilibrium thermodynamics we have to consider equilibrium. Now what does entail. That means that we are thinking of, say, for a simple system. In a simple system, we are considering, say, chemical work, mechanical work, and thermal work, right? So heat input is also considered. So when we are talking about a system which is in thermal equilibrium with the surroundings, we know that the temperature has to be the same, right? Temperature of the system has to be the same as that of the surroundings, as long as the wall between the system and the surroundings allow heat transfer. Now, if there is heat transfer allowed, the system and the surroundings will finally arrive at the same temperature T at thermal equilibrium. Now, as you know, in Clausius inequality, what we have learnt, ds is greater than equal to delta Q by T, right? Now, think of heating at constant volume. I am heating a system at constant volume. Now, delta QV, okay, so there is no non-expansion work, okay, no non-expansion work, and we are telling that heating at a constant volume, right? So now you have no non-expansion work, means there is no chemical work and stuff, and also expansion work also is like changing volume, right? But we are doing heating at constant volume, so delta QV is going to be just T, right? Changing internal energy. Now, as you can see here in Clausius inequality, what we are telling is now ds is greater than equal to delta Q by T. Now it is at constant volume, so we are telling it is greater than equal to delta QV by T, which basically means that this is greater than equal to du, and that's exactly what we have written, right? At constant volume, it is ds is greater than equal to, so I just, so I don't know, you don't get confused. As you can see here, at constant volume, ds is greater than equal to du by T, or TdS is greater than equal to, this is all coming from Clausius inequality, right? TdS is greater than equal to D. Now think of this, if we assume the internal energy to be constant, that means du is equal to 0, then TdS is greater than equal to 0, or ds is greater than equal to 0, right? If you consider t greater than 0, then TdS greater than equal to 0 means ds is greater than equal to 0, but ds is greater than equal to 0 with what are the constraints? Volume is fixed and volume does not change, internal energy does not change. So if volume does not change and internal energy does not change, now we get a very interesting corollary of the Clausius statement, right? We get of Clausius inequality, that the entropy, either ds can be equal to 0 or it is greater than 0 at, if the system is at constant energy and constant volume, right? Now you can also think the other way. Say for example, I fix ds, means at constant entropy, then what happens? The ds equal to 0, so du is less than equal to 0, this implies, but what are the constraints? ds equal to 0 and dv equal to 0, that means du s comma v. Now you see, in one case you are telling that if you take a constant internal energy, that the internal energy of the system is constant, then ds u comma v is greater than equal to 0. See, we are focusing on the system here, right? And another is constant entropy process. Constant entropy means where the entropy does not change, entropy is kept fixed, volume is kept fixed, then du has to be either equal to 0 or less than 0, right? These basically give me two extremum conditions, right? It gives me that at equilibrium, the ds at for a given internal energy and volume, the ds has to be either equal to 0 or greater than 0, right? And at constant entropy, du has to be less than 0 or equal to 0, right? So now think of heat transfer, that is taking the heat transfer that is happening at constant pressure. Now when you take constant pressure, we have already discussed this, delta Qp. So delta Qv, when we write delta Qv equal to D. Similarly, delta Qp equal to Dh. Now TdS has to be, again Clausius inequality comes in. So TdS greater than equal to dH. Now if you think of constant enthalpy, that means dH equal to 0, then ds, right, change in entropy at constant enthalpy and pressure should be equal to greater than equal to 0, right? Now again, if we go to constant entropy, that means ds equal to 0 and you have this constant pressure, so dH s comma p has to be less than equal to 0, right? Again you get two different conditions, right, from Clausius inequality. Now it is in terms of changing enthalpy and changing entropy. Now if you see TdS greater than equal to du gives you another consequence, one very interesting consequence, which is du minus TdS is less than equal to 0, because TdS is greater than equal to du. TdS greater than equal to du since TdS greater than equal to du, therefore du minus TdS is less than equal to 0. Now see, I define a new thermodynamic function or thermodynamic variable called f, which is Helmholtz free energy. I will soon show that how all of these potentials are connected, all of these different thermodynamic functions are connected. But you see, with this definition of du minus TdS less than equal to 0, I can define something called f, which is basically called Helmholtz free energy, which is U minus Ts, right? F equals to U minus Ts. Now this is called Helmholtz free energy. So this is another type of energy. So we have now encountered there is U, then we have H, and then you have S, and with using U and S we can define F, which is the Helmholtz free energy. And then with H and S, so as we have done already, so DH, TdS is greater than equal to DH, right? TdS is greater than equal to DH. So since TdS is greater than equal to DH, right? So DH minus TdS has to be less than equal to 0. So G, we defined another type of energy, which is called Gibbs free energy, which is G, which is equal to H minus Ts. We will show the equivalence of that, and we will show the equivalence of these different statements of entropy maximization and energy minimization, or Gibbs free energy minimization, or Helmholtz free energy minimization. But what you can see here is that by using simple Clausius inequality and focusing on the system and thinking of different constraints, like adding different constants like constant volume heating or constant pressure, heat transfer, we can basically define different forms of the Clausius inequality. And we can also define different functions like different new thermodynamic functions or new thermodynamic energies, which are like Helmholtz free energy or Gibbs free energy, right? Now we can tell, since du minus TdS is to be less than equal to 0, so we can tell, and here what we have talked about when we talked about du TdS, so we told that the volume has to be fixed, right, and temperature has to be fixed, right? If you see that, volume and temperature, so basically instead of volume and entropy, we are now telling volume and temperature. And if I do that, F is basically equal to U minus Ts. So dF, if I look at dF is du minus TdS minus SdT. Now when I am defining dF, we are telling there is a heat transfer at constant volume, right? So heating at constant volume is involved. Now if I tell constant temperature, then dt is also equal to 0. dt equal to 0, that means constant T. So now du minus TdS less than equal to 0 means dF at constant temperature and volume less than equal to 0, right? So this is another way of writing the same Clausius inequality, right? This is again indicating thermodynamic, the same thermodynamic equilibrium. Now, if you think of this, here what we have used is constant temperature and volume, but previously we used constant entropy, right? When we talked about du less than equal to 0, we told constant entropy and constant volume. Here we have replaced it by constant temperature and constant volume. Similarly, when I look at TH, say G, let us look at G. So G is H minus Ts. So dG equal to dH minus dDs minus S. Now dH is du plus vdP plus vdV minus dDs. Now think of constant pressure. So here dP equal to 0 and constant temperature at T equal to 0. So then what you basically get is dH minus TdS less than equal to 0 implies that it's constant pressure and at constant temperature. Now if you tell also constant temperature, so what does it mean? It means dG T comma P, right? T is constant, P is constant, P is less than, right? So we get another form where we now, so in dF, what we when we looked at Helmholtz free energy, what we tell that the change in Helmholtz free energy should be less than equal to 0 at constant temperature and volume, right? dF TV, right? So we told dF, this basically tells you dF T comma V is less than equal to 0. Now if you fix temperature and pressure, then the convenient way is to express dG T comma P is less than equal to 0. So this leads to a very interesting and nice approach, and this is an approach that was initially established by Callan and in his classic text it is described in detail, Thermodynamics and Introduction to Thermostatistics. And recently again using this approach of defining potentials, there is this book by Long-King Chen, Thermodynamic Equilibrium and Stability of Materials, in Springer, very recent book. All of these, both these books, basically this is the classic text where Callan introduces this postulatory approach, where basically or axiomatic approach. So where there are some axioms that are given, and we assume if we tell that these are true, then all the laws, the first law, second law, third law, in accordance with those laws, these axioms follow these laws, and we can show that we can use these axioms to understand these different types of thermodynamic equilibrium, right? So that is the idea. Now, before we go to complex systems is where you have like magnetic work, electrical work, and all the surface contribution from surface, etc. We will start with very simple system, right? We are always, in all these cases, we have been considering simple systems. Simple systems means we consider there is a thermal contribution to energy, there is a mechanical contribution to energy, the total energy, thermal contribution, mechanical contribution, and chemical contribution, right? So now, if you think of that, then if you look at these books, you can understand. Here, I basically following this axiomatic approach that is given by Callan, and what we can define here is entropy, or given by Long-King Chen recently. So basically, what is thermal matter? Thermal matter is basically given by entropy, and mechanical matter is given by volume or change in volume, right? If there is a mechanical work, there is a change in volume. If there is a change in, if there is heat transfer involved, then there is a change in entropy, right? So entropy, the total entropy of the system, is the measure of thermal matter. Volume is the measure of mechanical matter, and mole number of species, say species ith species. So it can be a multi-component system. We can have species 1, 2, 3, 1, 2, 3, or A, B, C, and each of these can have some mole numbers, right? Mole numbers is number of moles or amount of species, and that that number of moles of certain species I is basically measure of chemical matter contributed by species I, right? So the mole number is the measure of chemical matter, a mole number of species. Volume is the measure of mechanical matter, and entropy is the measure of thermal matter, right? Now, if we define that, and what we told that we'll define some, now what we can think of is that we define something like potential, right? There are different, so we look at like thermal potential. What does thermal potential mean? We will come to that. If you look at the very standard analog of electrical matter and electrical energy, then it becomes very easy to understand. Say for example, electrical energy is UQ, energy due to charge, right? UQ, and electrical matter is charge, Q. Now electric potential phi is UQ by Q or DUQ dQ, right? So this is something that we are very familiar, right? Electric potential, which is basically change in electric energy with change in electric matter or change in charge, right? So that is basically going to be the electric potential. Similarly, we can define thermal potential. How? You have thermal energy, which is say T, right? That is the thermal contribution to the total energy. Okay, total energy is U, and since we are considering simple system, so we can think of U is basically decomposed into UT plus UM, that is the mechanical contribution, and then UC. UC is the chemical contribution. Now, if you have thermal energy, which is UT, right, and then you have thermal matter, which is S. The thermal potential is del U del S, which is basically T. We have shown that, right? du equals to ds minus p dv when we did the combined first and second law, and when we looked at the exact differential and compared the coefficients, del u del s indeed is T, right? For a given del u del s for a given v and for a given n is indeed T. So thermal potential is del u by del s. Okay. So similarly, we can write, say, mechanical potential. Now, if you see what is mechanical energy is UM, which is basically PV work, right? You can think of PV work or force times displacement, right? So that's mechanical energy, and you have mechanical matter which is equal to V, and you have mechanical potential which is P, which is UM by V, or more accurately it is change in mechanical by del V, right? TdS. So, and there is a, so this is minus P in general. So minus P is equal to del U and del V, right? As pressure increases, volume decreases. So if you think that way, so there is a minus sign, right? So minus P equals to del U and del V. Similarly, we can think of chemical energy. Okay, this is basically because of chemical interactions and because of the species that come in, right? They form bonds and stuff. So that's the that gives you rise to chemical energy, and chemical energy, let's call it UC. Okay, and chemical matter is, so if you think of a single component system, we can think of the mole number of single that component to be N, then chemical potential we can now define, and that chemical potential is UC by N, or more accurately it is del U C. So in this case we are taking basically S, and so thermal matter is kept constant here and N is kept constant here, and this is basically del U by del N, and what are kept constant? S and N, right? So this is how we can define these potentials, and then once we have defined these potentials, then we can basically think of stating the thermodynamic problem. What is the thermodynamic problem? The thermodynamic problem is in general this. So you have different say think of this. You have different phases, and these phases share some phase boundaries, and you want to find out the equilibrium between the phases. Now, instead of thinking of phases, we will come to the exact definition of phase, but what I am thinking is phase as subsystem. So you already know about an isolated system, open system, closed system. Now let us think of a isolated composite system. So something like, I will just change the color in. So if you see, I am thinking of an isolated system. Right? In that isolated system, I am thinking of two subsystems. Okay, like say a subsystem alpha and subsystem beta, and I am also telling that this isolated system, it is completely isolated. Completely isolated means there is no heat and mass transfer that is happening between the system and surroundings. But this is a composite system, right? It has two subsystems. This is alpha subsystem and there is beta subsystem, and then there is this wall, right? This is the wall. Now this wall or constraint, what can this be? This wall can be flexible or rigid. This wall can be permeable to transfer of matter or impermeable. So wall basically gives you constraints, right? If it gives you constraint of rigidity, and if you remove the constraint, it becomes flexible, right? It is flexible means it is adaptable to volume change, right? It adjusts, right? If there is a difference in volume and if there is some work done, then basically it is flexible, so it will adjust the volumes by moving the flexible wall. However, if it is rigid, the rigid wall cannot move, right? So rigidity is a constraint. Flexibility basically removing the constraint, right? Wall can be flexible, wall can be rigid. Wall can be permeable. Permeable means it allows the matter to flow through the wall, right? Matter to flow through the wall between two subsystems alpha and beta, between the subsystems that we have considered, right? Now it is flexible, it is permeable. Then there is another thing which is basically allows heat transfer between alpha and beta, and that is basically diathermal. And if I now use a constraint, then that is basically adiabatic. Now this is a simple system, right? We are considering only what are the constraints, what are the contributions we are considering. One is thermal, another is mechanical, and another is species, right? The mole number of species, right? So for example, so if you think of this, so if I am just thinking of the same two subsystems. So here we call this subsystem 1 and this is subsystem 2, or you can call them alpha and beta, whatever be the naming convention, or you can call it like Roman 1, Roman 2, it does not really matter. So whatever naming convention you propose. Now you see, in subsystem 1 you have internal energy, you have volume, and you have mole number of different species, right? You have species 1, species 2, species 3. You can think of like different species like 1, 2, 3 or A, B, C or whatever you think of. And now you have, please note that these are all extensive variables, right? These are all variables that depend on the extent of the system. That's why I remove the. So you should understand that we are describing with three extensive variables. One is U, one is V, another is N, and N for different species. So it can be a multi-component system. So you have N1, which is the mole number of species 1 in subsystem 1, and then you have N1 in subsystem 2, that is the mole number of species 1 in subsystem 2, right? Which are different, which can be different, right? And then you have, say, another species called N2, which is in 1. The mole number is N21, and here it will be N2 in 2. Similarly, you can have Ni in subsystem 1, and you can have N. So you have like many components Ni in subsystem. right? And then this entire system is isolated. However, this is a composite system, right? It's an isolated composite system. Now we want to see, so we can initially make the wall completely constrained, like it is rigid, it is impermeable to matter, right? Matter flow. It is impermeable to the flow of species between the subsystems. It is rigid. It cannot move, and it is also adiabatic. That means it does not allow heat transfer between the subsystems. Now I remove all these constraints, and after I remove all these constraints, what will be the final state of these different subsystems, these two subsystems, right, which are in contact, right, when we remove all the internal constraints? That gives me the equilibrium states, right, the equilibrium states of these subsystems, right, and that is the goal of, that is the major goal in thermodynamics, right? If you look at phase equilibrium, that's the problem. So think of these subsystems as phases. Again, we can think of this as phases, and I don't give the concept of reservoir right now, but I'm thinking of, like, you have one phase alpha, and then you have another phase beta, right? Now if I want to define alpha and beta, so if I define a phase, what is phase? A phase by itself is the portion of matter that is chemically homogeneous. Chemically as well as structurally homogeneous, and right, chemically as well as structurally homogeneous, and it has, it's physically distinct. Physically distinct means distinct physical characteristics. So for example, density, refractive index, the heat capacity, and all these things are distinct, right, for alpha and beta. Now physically distinct, chemically homogeneous, and then mechanically separable. Now we have, for example, we have separated them, and we can separate them by doing some mechanical work or some such process. I'll come to this mechanically separable in some later also. So when we discuss physical, multi-component, multi-phase systems, but here we are also considering exactly that's a problem. So this alpha phase is like a subsystem which has its own internal energy, say U alpha, and it has V alpha is a volume, and it has also these different species, U alpha, V alpha, Ni alpha, and so here it is like U beta, V beta, and Ni beta, and this is the alpha system, and this is the beta subsystem, and we are trying to find out. And now overall I have put some, I have made it isolated, made them isolated. However, I put a wall or boundary or phase boundary between this alpha and beta, and this phase boundary can be such that it has all these constraints like rigid and impermeable and gravity. But I am removing all these constraints, and then I am trying to find out what will be the equilibrium state, what will be the final state of the, when we remove all these constraints, and that final state is going to be the equilibrium state, and the equilibrium state of alpha phase in equilibrium with beta phase, right? So alpha phase by itself is homogeneous, beta phase by itself is homogeneous, both of them come together. Now they have, although they are chemically homogeneous, they are physically distinct, that you initially have some alpha and beta, and now you want to put them together. Once you put them together and you remove all the internal constants, that means allow the phase boundary to be flexible, that means the phase boundary can move, you allow it to be permeable, that is the species can, there is exchange of species through the wall, right? It allows exchange of species or flow of species through the wall, and also diathermal, that is, it allows heat transfer to the wall. Then you want to understand the equilibrium conditions of alpha and beta, and that is exactly the problem of phase equilibrium, right? That is exactly the problem of phase equilibrium. Now to solve it, you have these different postulates and these are axioms, and one of these axioms is that you have an entropy function S, which is defined for all equilibrium states, right? All equilibrium states, which is a function of these extensive variables u, v, n. Extensive means they basically, so S itself is an extensive variable and it's a function of other extensive variables u, v, and n. So so defined for all equilibrium states, and this is the values are assumed by the extensive parameters in the absence of the internal constraint are those, right? The extensive parameters u, v, n are those, the values that are those that the values will be such that it maximizes the entropy over the manifold of constrained equilibrium states. So that is the most important point, that the entropy, basically the subsystems will assume values of u, v, and n such that the total entropy of the entire composite system is maximized, okay, over the manifold of all these different constraint equilibrium states. So basically, in absence of an internal constraint, remember this point, that you have the wall can give you constraints. Now if you remove these constraints, then basically the values assumed by u, v, and n will be such that the entropy of the total system is maximized, right? Or change in entropy. So the total system entropy is maximized. Again, it has come from the same thing like ds u comma v. So this is basically, in one sense, we are telling that there is a function s in such that ds u, v, and n has to be greater than, right? It is maximized. Now, by the way, if I look at this function, so basically if I look at entropy as a function, and if I look at any function which is to be maximized, how we find maximum minima? We first find out ds equal to 0. That is the extremum condition. Once we know the extremum condition, then we want to find out whether the second derivative is going to be negative. If it is negative, then obviously entropy is maximized, right? So again, we will go into these definitions more minutely. So for example, S is an extensive property, that means it's additive, that we have already proved, right, from second law. So this is something that we are telling, it's a slightly different approach, but we are telling that S is the function, and this is a function of u, v, and n, which are also extensive parameters, right, of the system. Like u is the internal energy, is extensive parameter, volume, extensive parameter, right? This is not molar volume, this is not molar internal energy, this is total internal energy, total volume, and the mole number, right? These are all additive, and therefore S is also additive, and total S of a composite system is sum of entropies of constituent subsystems. So if you have subsystems alpha and beta, it is nothing but S alpha. S is nothing but S alpha plus S beta. Right? So that's what I have done. Summation over alpha for all the constituent subsystems. And entropy of each subsystem is a function of the extensive parameters of that subsystem. Right? If S alpha, if I consider F alpha, S alpha is a function of U alpha, V alpha, N1 alpha, and it's multi-component, say up to N1 to Nr. So you have species 1, 2, 3, 4, R. So basically, if you think of 1, 2, 3, 4 R, you will tell what is 1, 2, 3, 4 R. These are nothing but, say, for example, copper, aluminium, niobium. So you can think of, like, say, some elements, or you can think of some compounds which form the components of the system, right? Chemical components. These are different chemical components. So you can have one component system, like you have like a unary system, or you can have a multi-component system where you have multiple components, like, and each component has its own mole number, right, in each subsystem or in each phase, right? Another very important thing that we will come to in so I'll describe all of this in detail in the next class onwards. So I have talked about what is the problem. Thermodynamic problem is finding the phase equilibrium, right, where you or finding the equilibrium states of this isolated composite system, okay, in which you want to be, and the equilibrium states are such that the entropy of the total entropy of the whole composite system is maximized, right, after removing the in the absence of the an internal constraint, right? So that is the thing. So, and the entropy is continuous and differentiable. So this is also a very important part of the statement of the axiom, that entropy is continuous and differentiable function and is monotonically increasing function of energy. Energy means internal energy, right? So we will continue in the next class about this. So in the next lecture, I'll continue about this, and we will talk about the other two postulates or other two axioms. Right? This is an axiomatic approach. So we have these postulates, and we will see that these postulates finally are in such a way that no thermodynamic law is violated, and you get back the equilibrium state of this multi-phase, multi-component system, or this isolated composite system containing many subsystems, right?